key question of both practical and basic scientific concern that hill slope hydrologists and geomorphologists can answer is whether or not a landslide is going to happen. So we talk about gradual creep, and that's something that we're concerned about for agricultural sustainability due to tilling of the land. We're concerned about it because it might eventually affect telephone poles, and we also just want to know what the general rate of sediment delivery to rivers is going to be. In hill slope creep, moving mostly soil is largely going to move finer sediments into the rivers, the kinds that are typically held higher in the flow and contribute to water quality and clarity, but don't necessarily form the bed and banks of the rivers. On the other hand, landslides can access deep material that hasn't been weathered as much, and this material can importantly be significantly coarser and affect the rivers and affect other regions wherever that material moves. Furthermore, landslides are, for obvious reasons, major hazards. Even up here in Minnesota, we have significant landslide hazards. I've been part of a project funded by the state to characterize and map landslide hazards over the past few years. And as we continue to see larger rainfall events, we see more and more landslides. And so that's one of the things I want to answer today is, why do we see more landslides when it rains? And what is actually the force balance involved, or in this case, the stress balance involved in determining whether a landslide will happen or not? And the stress balance is really, can just be summarized as this, where we have some sort of driving stress here. And some sort of resisting stress here. If the resisting stress is greater than the driving stress, then no landslide will occur. If the driving stress is greater than the resisting stress, then a landslide can occur. And actually, it's probably quite likely that if that driving stress is greater in any way, the landslide will occur, and then that'll all be over with. So we won't have a stable landscape with driving stresses being greater than resisting stresses. Where those two are perfectly in balance, that's what we call incipient failure. So that's at the point at which we could be, at which every single piece of driving stress is perfectly balanced by any resisting stress, and the single footprint and step of a small mouse, a butterfly landing, a piece of pollen falling on the hill slope is going to be enough to cause that whole thing to fail. In reality, the system is not quite in such a perfect balance like that. It's very heterogeneous. But if we're simplifying it like this, we can think of the incipient failure as the point of the stress that is going to be associated with that actual hill slope failing. Because once it's even the tiniest bit above it, a failure will happen, and then the hill slope will be modified to such a point that we're back below the failure stress on the remaining part of the hill slope. So, by the remaining part of the hill slope, what I mean is that the steep part is going to fail. And then, whatever's left behind shouldn't be as steep or shouldn't be as likely to fail. So above we had drawn that free body diagram with the block on the inclined plane, and we can use that to start thinking about the stresses involved in landsliding. I'm going to redraw that again below. But the idea here is that we have this term that I'm calling sigma sub g, which is the weight of this block. And so here, rho is density, g is gravitational acceleration, is approximately 9.8 meters per second squared. And as you might recall, I often just call that 10 meters per second squared when I'm doing back of the envelope calculations. It's just really nice to be able to do that sort of thing in your head without needing a computer or calculator. Unless you're way better at mental math than me and like to carry a lot of decimals, I usually just like to know what's roughly going to happen. And h is going to be the thickness. Of that landslide block. And so if we look at the units of all of these different terms, so density is mass per volume, so kilograms per meter cubed. gravity is meters per second squared, and so this is an acceleration. And then h is the thickness. And so let's see, we have a 2 meters up here. That gets rid of that, and so then we end up with kilograms per meter second squared. And the units, if we think about force, that's going to be units of newtons. And the base SI units for that, though, for Newton, is kilogram meter per second squared. And so you can think of this stress as, and I'm going to just throw that down here so we have a bit of space for it. It's going to be newtons per meter squared, and that's where we get force per unit area. And so if you ever kind of forget what a stress means, just go through the units and you're going to be able to figure it out. So here is a planar landslide, and so this is one of these translational failures, right, in which we're going to have some sort of slip. Oh, for goodness sake, can I ever draw a straight line? Let's call that, oh, that's terrible, isn't it? Let's call that approximately good enough. So that's where that failure is going to happen. There's some sort of density of this material here. There's gravity pulling downwards. The actual thickness of this piece of material up here is going to be h, and that's going to extend from the top here to the bottom over here. So we have rho gh. We're going to have an angle down here that I'm going to call alpha. And so therefore right here we're going to have rho gh equals sigma sub g, which is going to be facing downwards. And then this stress causing this failure is going to be sigma sub d, so this driving stress. And then we're going to have a stress that's actually resisting this failure, which I'm going to call sigma sub r. And so those two are exactly this driving stress and resisting stress that we have above right here. Ooh, let's make this full screen so it's a little nicer. You can see a bit more. There we go. So altogether, as I mentioned above, this gives us kilograms per meter second squared, and that's our, again, stress units. And this is usually where I would make a joke about stress and strain and failure and the way that the semester goes. Especially considering that it's 2020, I'm just going to mention that I would make that joke, and I'm not going to say anything about it. We're going to move on. So, question here though is what is rho? So rho is density, and it's going to rho together comprises the solid material. So let's say that we have some sort of rocky material that's in that, but then we might also have some little pores and fractures going through it, and so those fractures might be filled with air, or they might be filled with water. The density of air is so much lower than the density of rock or mineral material that we can just assume that air is about the same as vacuum and not really consider it. But water actually has a density that's pretty close to the density of rock. So, for example, density of granite is equal to 2,700 kilograms per meter cubed. And so remember, kilograms per meter cubed, that's just what we had above when we were doing the dimensional analysis, looking at the units. Whereas rho water is equal to about 1,000 kilograms per meter cubed. And so these two are actually much more, relatively similar. They're the same order of magnitude, so we have to think about them as well. What we could do up here if we wanted to, all right. There we go. So what we could do up here if we wanted to, so we have rho is equal to this term here, which is the rock term. And this over here, lambda p is just the porosity. So we have 1 minus lambda p times the rock density plus lambda p times Fw times rho w. So this is going to be water density times porosity times the fraction of pore space flooded. I'll just say flooded with water. And then if we wanted to, we could do something like also add plus, lambda p 1 minus Fw rho a, if we wanted to have some sort of air term attached. But we're just going to draw a big line over here. Air is negligible. You could, if you want to, for completeness and correctness, and you absolutely might want to, and you can imagine other situations, like if you're solving for mass failures on a different planet with different materials, it might start to become important what the gas phase is doing. But on Earth it doesn't. So the next thing that we want to do then is so now that we know what this density is, the next thing we're going to want to do is to be able to split the sigma sub g, so this is the gravitational downward stress, into the shear stress and the normal stress. And so here I've actually missed a line break, so I'm going to draw a vertical line right here. And in fact, I'm going to draw a vertical red line just to make it really clear those are two separate equations. So this is going to be sigma here is going to be the normal stress, and tau here is going to be the shear stress. And so what we have is cosine theta and sine theta. And so over here, I did kind of a classic Andy move. I often use alpha, but I think I ended up using theta this time around just because of how commonly that's used in textbooks and so forth, and I think it might be used in Anderson as well. So this is going to be theta or alpha, but mostly theta. So we have cosine of theta is going to give us the portion that's perpendicular to that plane, and tau is going to give us sine of theta, which is parallel to that plane. So again, if I just draw this plane right here, look at this plane right here, we have something like I'll just do it in green, sure. We have this, which is going to be sigma sub g cos theta. And then we have this over here, I'll move it into red, sigma sub g sine theta. And that's equal to tau. And this is going to be equal to what we call sigma by itself. So normal stress and shear stress. So at this point, once we have this, we can fully characterize the driving stress, because the driving stress is just this tau term. And so that tau term is just going to be the gravitational stress times the sine of theta. And so that means that we have this right here, which is just this density term, that's just rho g h sine theta. Perfect. So what remains to be done is to add some modifications to the forces resisting the stress, so the sigma sub r, based on friction, pore fluid pressure, and cohesion. And so we're going to go through these in order 1, 2, and 3. So if we have a cohesionless material with no water content, we can calculate the resisting force very easily. It's just completely analogous to that frictional force from the block on the inclined plane from your introductory physics class. So we just have, in this case then, mu, which, as you might remember, is coefficient of friction. Well, the coefficient of friction if I actually use articles in English properly. But the coefficient of friction is mu, and that is typically for earth materials approximately 0.6, and this is per Byerlee's law. If we, and Byerlee's law is just an empirical relationship from a whole bunch of experiments that were done, I think mostly at MIT with a student of my former undergrad advisor, Brad Hager. So the student's name was obviously Byerlee. So then if we take that, then this term right here looks exactly the same as the term in the shear stress, the driving stress, and that this is just going to be, again, the density, and then gravity, thickness, cos theta instead of sine theta. Great, okay, so then this is really easy. This is where we get to that place at which we can just cancel out the rho gh, and if we try to set these equal to each other, and we can very, very easily figure out the angle at which failure might occur. And so if we do that, and I'm just going to do this in the margin right here, if we say sigma d equals sigma r, then we have basically, that means that we have this term right here, gh. We have the same terms on this side of the equation, so we don't have them, so that both of these can cancel out. And so what we just have then is that sine theta is equal to mu cos theta, or mu equals tan theta, and that's how we can actually solve for the angle of repose for a dry granular material. We can figure out what angle for the given coefficient of friction, and this is then, in this case, you can think of this as internal friction, internal to that medium. So at what angle will we start to see failure? And that will give us what we call then the angle of internal friction, which on a hill will give us the angle of repose. And so that's if we imagine that we have a sand mound here with theta right there. And we're at the kind of point at which grains are just starting to avalanche down the sides, but maybe arresting, maybe not quite. We're at incipient failure on all hillsides. And so you can imagine this like if you're just pouring sand grains onto the top of this hill from some sort of cup and just letting it evolve. And that's how you get to that angle of repose. And so many steep hill slopes will never be able to get steeper than this angle of repose, because then they'll start, spontaneously failing. All right, so after this, so this is just the dry hill slope. But one of the questions I motivated this with is trying to understand, why is it that we end up seeing landslides when it rains? Well, let's think about what water does to that hill slope. So first off, I just want to mention that like a tiny amount of fluid in the pores of sand can actually increase cohesion between the grains, and this is because of capillary or pendular forces. These the surface tension of the water there. Any additional fluids will actually decrease the resisting stress by reducing the effective weight of the particles on the hill slope, and that's by buoyantly supporting them. And so you can think about it as the same way as like if I'm standing on solid ground on the Earth's surface, I feel pretty good. But if I'm underwater, you can kind of touch the bottom, but you feel yourself bobbing around. And that's because we are, not that much different in density than water. I'm only a little bit denser myself than water, I believe, depending on how full my lungs are. And so you don't actually have that normal stress holding yourself in place, and you end up just bobbing around. Similarly, if there's sand that's underwater, that sand goes from a density of 2650 to an effective submerged density of 1650, so dropping off that 1,000 kilograms per meter cubed of the water. And so because it's being partially buoyantly supported, there's actually less normal force to create frictional resistance. And so because of this, we can think about how much those pore fluid pressure terms are important. So we'll have this pore fluid pressure term, but then we're also going to have a second term. So pore fluid pressure. But then the other term that we're going to have to include and have to consider is weight, right? Because the water actually adds mass to the block. So here we are, we're going to define an effective stress, which is the sigma term, so the stress minus the pore fluid pressure term. This first one here, now we have, this is just the mineral density, rho mineral. This right here is going to be the rho water. So this is the extra density added in from water. And that's the exact same thing that we're talking about up here. But here, we're only considering such a teeny tiny itty bitty amount of water that it's not actually affecting either the cohesion or the pore fluid pressure that might be affecting its stability. So this is basically meant here, in this case, it has, for this solution to be true, it has to be negligible. Or we have to have this water be replaced by something that's, non-polar and doesn't have any ability to cohesively connect those grains, and also be very small in volume. So we have this water, and then we also have here this minus term, and this is the PF, the pore fluid pressure. And that's what's adding buoyancy. And what you can see here is that all of this extra water density impact is canceled out perfectly by this pore fluid pressure. And therefore, what we end up getting is that the effective stress, the effective normal stress, is just going to be this rock fraction times, whatever portion of this isn't porous, times gravity, times thickness of the material. And so therefore, this effective normal stress is going to not include any of this additional weight of the block. And therefore, we don't have any extra advantage in creating additional normal forces to increase the friction. However, the shear stress includes this term and does not include the water pressure because the pressure is isotropic, so it's always acting normal in whatever direction and it is never acting in shear. And so then if we think about what might be happening then, we're going to have, and I'm going to just write it up here, we're going to have, in this case, tau is going to equal the same as above with the water. So this pore fluid pressure term is actually causing there to be excess shear stress with respect to normal stress. And so therefore, and this is exactly what I'm writing here, that exactly negates the additional weight of the block when computing the frictional resisting forces, but not when calculating the driving forces. So then wet leads to failure. All right, so that's why landslides occur in the rain, because the rain actually will cancel out the normal forces, but won't cancel out the shearing forces. And so the third component that we want to think about, though, is cohesion. So there's something else that might hold a hill slope together. And these are stresses that can, just like keep this material glommed together, whether it's root fibers, clays that are sticky, interlocking rocks of irregular shapes that are able to, bind together. And therefore, what we have here then is that this resisting force is going to be this mu times sigma effective cos theta plus this sigma sub c term. and the sigma sub c term is the cohesion. And it often is represented by some other characters, things like S, but I'm keeping it sigma because it is really a stress, just to kind of keep that clear. And we can then combine that with the driving forces to say that the point at which a hill slope is at the point of incipient failure is when tau here, so shear, driving, stress, is equal to this whole thing here, which is our resisting stress.